Hey guys, in this video we are going to solve the following worksheet that covers sections 1.6 through 2.3. We have some limits here. We have a little bit of continuity, a limit definition of derivative, and a couple of derivatives at the end. So let's start. Let me copy the down quickly. Let's find the following limit. Let's try to bring that limit into the following form, where we have sine of x over x. So we need to move from cosine of pi over x to sine. This can be done using the following trigonometric identity. So sine of pi over 2 minus pi over x is going to be equal to cosine of pi over x. All right, now let's factor out pi. And let's see what we are going to be left with. So we have sine pi multiplied by 1 over 2 minus 1 over x. So this is x minus 2 over 2x divided by x minus 2. All right, now it seems that it's more or less of this form of sine of x over x. So the angle that we have here should appear in the denominator. Let's try to artificially bring this into this form we have here. So we have a limit when x is approaching to 2 of sine pi x minus 2 over 2x. So I need the same term in denominator. So we will artificially multiply and divide by pi. Then we are also going to multiply and divide by 2x. So multiplied by 1 over 2x. Okay, now let's see what we're left with. Now you can see that here you have the same angle. You can use substitution to call it theta. When x is approaching to 2, then you can see that we have theta approaching to 0. So basically we have limit when theta is approaching to 0 of sine of theta over theta, which is equal to 1. Right, so that limit is equal to 1. This is pi, and this is equal to 1 over 4. So the answer is then pi over 4. Okay, now next problem. Let me copy it down. Okay, next problem. Let's find the following limit. So we have this ugly denominator which goes to 0. Let's try to get rid of it. Let's again try to bring this into the form of sine of x over x. So we know that tangent of x can be expressed as sine of x over cosine of x. That's where we are going to get our cosine of x. But before moving on, we need not only sine of x, we need sine of x minus pi over 4. So let's recall the formula for tangent of difference of two angles. If we have tangent of x minus pi over 4, then it is equal to tangent of x minus tangent of pi over 4, which is 1 divided by 1 plus tangent of x multiplied by tangent of pi over 4. So this is tangent of x. Okay, great. So we can replace a tangent of x minus 1 as the following product. Limit when x is approaching to pi over 4. Tangent of x minus pi over 4 multiplied by 1 plus tangent of x. So this term is fine, since if we substitute pi over 4, we'll get 2 divided by x minus pi over 4. And we also said that we are going to expand this as sine of x minus pi over 4 over cosine of x minus pi over 4. So we'll end up with the following limit. Sine of x minus pi over 4 divided by x minus pi over 4 multiplied by 1 plus tangent of x multiplied by 1 over cosine of x minus pi over 4. Again, this term is fine. If we substitute pi over 4, we'll get 1. So no danger here. Right now, that goes, this limit is equal to 1. This limit is equal to 2. This is also equal to 1. So the answer is then 2. Okay, great. If I did miss anything, yeah, it seems it's okay. All right. All right, next problem. Cosine of, so let's find the following limit. Cosine of x minus sine of x over x minus pi over 4. Let's try to work with numerator a bit, and let's again try to bring this into the form of sine of x over x. So let's recall the formula for sine of difference of two angles. If we have sine of x minus pi over 4, then it is going to be equal to sine of x multiplied by cosine of pi over 4 root of 2 over 2 minus cosine of x multiplied by sine of pi over 4, which is root of 2 over 2. Right, so all we have to do then is we need to multiply this expression here by minus root of 2 over 2. So let's transform this in the following way. Minus, if we are going to multiply by 1 over root of 2, then we need to multiply by root of 2. So basically, you'll see it. You will see where I'm going, guys, in a second. So we'll have sine of x multiplied by 1 over root of 2 minus cosine of x 1 over root of 2 divided by x minus pi over 4. Okay, so we as you can see, we artificially multiplied and divided by minus root of 2, the square root of 2. So then that stuff inside of brackets can be expressed as minus root of 2. This is then sine of x minus pi over 4 divided over x minus pi over 4. Right, and when x is approaching to pi over 4, this goes to 0, that goes to 0, so this limit goes to 1. So the answer minus root of 2. Okay. All right, guys. Next problem. Let's try to multiply and divide by conjugate of denominator. So we will end up with theta squared of 1 plus cosine theta. Then in denominator, we have 1 minus cosine squared, which we are going to replace with sine squared of theta. So this is limit when theta is approaching to 0 of 1 plus cosine of theta, which is fine since this is simply 1 when theta goes to 0, divided by over by sine of theta squared, or let's write this down as sine squared or sine theta over theta, and this is squared. Okay, then when theta is approaching to 0, this goes to 1, and that goes to 2. Right, so the answer is then 2. Okay, next problem. All right, so use the intermediate value theorem to show that the equation x is equal to cosine of x has at least one solution in the interval from 0 to pi over 2. So let's express that as x minus cosine of x. Let's call this as a function of x. Then first of all, f of x is continuous everywhere, since x is continuous everywhere and cosine of x is also continuous everywhere. And then let's find value at 0. This is then 0 minus 1, so this is minus 1. And f at pi over 2 is equal to pi over 2 minus 0, so pi over 2. So we can see that at that point, the value of function is negative. At this point, the value of our function is positive, and 0 is in interval from minus 1 to pi over 2, meaning that our function has at least one solution, the interval from 0 to pi over 2. I mean, our function is equal to 0 at least one point in this interval. Right, next problem. Let's bring this into the following form. Sine of 6x divided by 6x multiplied by sine of 8x multiplied by 8x over sine of 8x. So we multiplied by 8 over 6 artificially. We have to divide it by 6 over 8. Then we'll end up with so the limit of that goes to 1, limit of that goes to 1, and this is 6 over 8. So the answer is 6 over 8. All right. Next, let's find derivative of 1 over root of x using the limit definition of derivative. So we need to find derivative of 1 over root of x. So basically, let's call our function of x as 1 over root of x. Then if you recall the limit definition of derivative, this is limit when h is approaching to 0 of f of x plus h minus f of x divided by h. So let's plug in the value of x plus h into our function of x. So we'll end up with 1 over root of x plus h minus 1 over root of x divided by h. Okay, so we will have a limit when h is approaching to 0 of root of x minus root of x plus h divided by h x x plus h. Let's multiply and divide everything by the conjugate of numerator. So we'll have limit when h is approaching to 0 of x minus x plus h. So minus x minus h divided by h multiplied by 1 over root of x x plus h multiplied by conjugate of numerator root of x plus root of x plus h. So this is minus h, so this is minus 1. Then if we substitute h equal to 0, we'll end up with 1 over root of x squared, which is x. Here we'll have again 2 root of x. So the answer is then minus 1 over 2 root of x, or minus 1 over 2 x to the power of 3 or minus 3 over 2. Okay. All right. Next problem. Let's find whether this function here is continuous and differentiable at the point x is equal to 1. First, let's check for continuity. When we substitute x is equal to 1, the value of our function is equal to 2. All right, now let's see whether this limit approaches to 2. It indeed approaches to 2. When we are approaching to 1 from the right side, we have limit of 2x, which is equal to 2. Okay, so that function is continuous at point x is equal to 1. Now let's check for differentiability at point x is equal to 1. We need to find whether the slope of tangent line when we are approaching to 1 from the left side is equal to the slope of tangent line when we are approaching to 1 from the right side. Okay, you can, guys, quickly check that without using limit definition of derivative by straightforwardly taking derivative of x squared plus 1. This is 2x. And derivative of 2x is then equal to 2. At point x is equal to 1, derivative of x squared plus 1 is 2x and is equal to 2. So the slopes of tangent lines are equal to each other, meaning that it is differentiable at point x is equal to 1. But we are going to show all the steps. So first, let's find a limit when h is approaching to 0 from the left side. F of x plus h minus f of x divided by h. We are checking for point x is equal to 1, so we need 1 instead of x here. If we add some value that is slightly less than 0, then we'll end up with a value of function f at point where it's slightly less than 1. So we have to use this this function x squared plus 1. So we'll end up with limit when h is approaching to 0 from the left side of 1 plus 2h plus h. So I'm opening the brackets right away, plus 1 minus the value function at point 1 is 2 divided by h. So these are going to cancel. So we'll end up with a limit when h is approaching to 0 of 2 plus h. So this is equal to 2. Now we need to find right hand limit when h is approaching to 0 from the right side. So the value of function at point 1 plus something positive will result in value function at point where it's slightly greater than 1. So we are going to use the following function, and this is then 2 1 plus h 2 1 plus h minus the value of function at point 1, which is 2 divided over by h. So then we'll end up with 2h over h. So this is equal to 2. So we have shown that these two one-sided limits that define our derivative, they are equal to each other, meaning that our function is differentiable at point x is equal to 1. Okay, next we need to check whether our function is continuous and differentiable everywhere else. So when x is less or equal than 1, we are working with this function. This is polynomial, it's continuous everywhere. When x is greater than 1, this is again a polynomial that's continuous everywhere. Okay. Next problem. Let's find an equation of the tangent line to the curve at the given point. So y is equal to x to the power of 4 plus 2 e to the power of x at point 0, 2. Let's first find the slope of tangent line. Slope of tangent line is equal to derivative at point 0, 2. So the derivative here is equal to 4x to the power of 3. So using the power rule for derivatives, plus 2 derivative of exponential is simply e to the power of x. So this is then equal to, if we substitute x is equal to 0, we have 0, and this is 2. The slope of tangent line is 2. Then equation of the tangent line is going to be y is equal to f at point x0, which is 2 plus 2 x minus x0, x minus 0, or simply x. So here's our equation of tangent line. Next, let's find following derivatives. Okay, first derivative is that we have x to the power of some real number. So it is equal to derivative of that is equal to e x to the power of e minus 1. Next, that can be expressed as x to the power of minus root of 10. So derivative of that is minus root of 10 x to the power of minus root of 10 plus 1. Okay. Next, let's find derivative of that. So that can be expressed as 3 over 5 minus 2 over 5 x to the power of minus 1. Derivative of y then is equal to 2 over 5 x to the power of minus 2. Okay, guys. That concludes our worksheet on sections 1.6 to 2.3. Thanks for watching.